Okay, this video is going to be over gas stoichiometry. Now, the reason that we have to do gas stoichiometry, we've kind of already talked about how we can convert gases from moles to liters or liters to moles using this 22.4 liters per mole conversion, the volume, molar volume. But the problem is a lot of times our conditions are not at STP. So remember that STP is your standard temperature and pressure. And most of the time when we're working with gases, we're not at that standard temperature, which is 0 degrees Celsius, or pressure, which is 1 atmosphere. So that's why we have to do it this way with gas stoichiometry. Another key thing is that because we are doing stoichiometry, that means you do need to make sure that you have a balanced chemical equation before you start your problem. So what we're going to do is we'll use stoichiometry to find our moles of gas produced, and then we're going to use the ideal gas law to find the volume. So remember, your ideal gas law is PV equals nRT. So we'll be finding our moles of gas here, which is N, right? And then we can use our information to find our volume of our gas. All right, so let's take a look at an example. Okay, so we have the volume of carbon dioxide produced. So we're calculating our volume of carbon dioxide produced. So this is what we're looking for. When 165 grams of butane react with excess oxygen, so that means it's not limiting. And here is our temperature and pressure for this particular problem. So first thing we want to do is we are going to use stoichiometry to find moles of our gas produced. So I need to go from my grams of butane to moles of carbon dioxide. So this is just straight stoichiometry like what we've done before. Before we get started though, make sure that your equation is balanced. In this case it is not yet. So we'll go ahead and do that. All right, so we're going to start out with our 165 grams of butane. So we have grams of butane here, and then we need to go to moles of butane. So we just have to look up or calculate our molar mass. So butane is 58.12 grams per mole. And then we can use our mole ratio now, so moles of butane, and we're trying to get 2 moles of carbon dioxide to go from moles to moles. So we have 2 moles of butane and then 8 moles of carbon dioxide. Multiply across the top, divide by what's on the bottom. We should have 3 significant figures here because this guy here only has 3 significant figures. And you should end up with 11.4 moles of carbon dioxide. So now that we have our moles, so that's our first step, right? Find our moles. Second step, we're going to use our equation, PV equals nRT. Okay, so we just found N here, so that's 11.4 moles. Our volume, that's what we're looking for. Pressure, it's up in the problem, that's that 1.1 atm. And then our temperature is 35 degrees Celsius. Don't forget that it needs to be in Kelvin, so we've got to add 273. And then R is the ideal gas constant, which of course will be given to you. All right, so we just have to plug it into our equation. So pressure times volume, and then N, R, and T. So solving for volume, we're going to look up at our initial problem for our number of significant figures, which for this case is going to be 2. So we have the 35 and the 1.1 both have 2 significant figures, so our answer should only have 2 significant figures. So when you round it, you should get 260, and then don't forget your units. For this one is going to be liters because we use the ideal gas law. All right, next, go ahead and do the next problem. And then I will make there'll be a second video for this problem. So do this problem, it is a limiting reactant problem, and then come back and check the second video to check your answers.